Hello again. Thanks for joining us. This is the Space Nuts podcast. My name is Andrew Dunkley, and joining me as always is Astronomer-at-Large, because he's got a very large brain. It's Fred Watson. Hello, Fred.
Thank you, Andrew. Hello to you too. Sometimes it's bigger than others, I have to say. Never mind, that's all right.
Well,
it's not about the size, it's about the grey stuff.
Yes, exactly right. And we're doing something different this week. This whole episode is dedicated to audience questions, which we do from time to time. We've got a whole batch that we want to get through. A few audio questions, a couple of written questions, but also questions from a live studio guest, Russell Palmer from Western Australia. Russell, hello.
Hello, everyone.
Welcome.
It's great to be here. I'm blown away to be invited on the show as Chief Inquisitor today.
Chief Inquisitor. We will probably do this from time to time now that we have the technology, and you're the first cab off the rank, the guinea pig, to see if this will all work for us. But we thought it would be nice for the audience, particularly those on YouTube, to see another face besides ours. I mean, they must be getting sick of us. Couple of spectacled old men sitting here just talking rubbish most of the time. Yeah, Russell, go on.
You could have done better than mine, I'm afraid.
Anyway, we will get to you shortly and have you and Fred have a bit of a discussion about a few of the things that are buzzing around in your brain. We're also going to hear from Evan in Sydney on the orbit of planets. Simon wants to know when a black hole is in fact a black hole. When does the stuff that goes into it become black hole? Martin from the UK is asking about light, or when there won't be any in the universe, which is, pretty morbid. Thanks, Martin. Appreciate it. And Sandy in Melbourne asking about what happens when he looks at the International Space Station from Earth and it's orbiting and it's blinking on and off. I'm guessing it's not nav lights. But we will tackle all of those questions on this edition of Space Nuts. Thanks again for joining us. So, Fred, by the way, how are you? Haven't had a chance for a chin wag.
Still alive. Yeah, all good.
That's good. Before when we started, and I told you that I rang Hugh and he would call.
He called right in the middle. There you go.
Hang on, I've put him off. There we go. So let's get into our first question. This one is from Evan in Sydney, who's asking about a question of a segment we did a little earlier, about a week ago, I think it was, about the orbit of planets. And here's his question now.
Hello, Fred and Andrew. This is Evan from Sydney. In today's podcast, Fred described a planetary system where many planets were in orbital resonance. This means that the planets must tug on each other at regular intervals. In our solar system, the spacing of the planets was described by Johann Bode and means that most of the planets are not in resonance. Which arrangement is more stable in the long term? Thank you.
Okay. Yes. Thank you, Evan. Fred, over to you, as always.
Well, yeah, actually what Evan refers to there is something called Bode's law. Johannes Bode was an astronomer who worked at the end of the 18th century, but the idea that he put forward had been proposed earlier by a man whose first name I can't remember, but his second name was Titius, a name to reckon with. And that says that effectively, with a little bit of numerical tinkering, each planet is twice as far away as the previous one. It doesn't quite fit that, but it's something like that. And that's what caused people to look for the first asteroid that was found, Ceres, back in 1801. People were looking for the missing planet because the Titius-Bode law has a gap where Ceres, just about where Ceres is, and so when it was found, everybody said, "Oh, that's great! This is a real thing. This law, it works." There's a planet where it was predicted to be, and actually, in fact, it had already had a good, a good tick before that, because in 1781, when Uranus was discovered, that was found to be where the Titius-Bode law predicted it would be.
So it's getting very bawdy, Fred.
Yeah, well, that's right. It's just it's a long, drawn-out tale, but it's not. These are not planetary resonances. They're, in fact, there's really the present view is that there's no physical reason why that should be. That it's something like a coincidence. Although I find it a bit suspicious when you've got a law that seems to work reasonably well. We've never seen it as it's stated in the solar system in an exoplanetary system. But what we have seen is what we were talking about last time, which was the resonances. So you've got these very strict ratios of planetary periods, the time it takes to go around one planet to another. And there was a resonance chain that we talked about with an exosystem whose name I can't remember. I think it was an HD star, that it was around Henry Draper star. And I think it was something like 18963. I can't remember the resonances, but they were, these are integral numbers. There are things like that in the solar system. In fact, there are resonances in 3 of the moons of Jupiter. There is a resonance between Neptune and many other Kuiper belt objects, including Pluto. Pluto goes around twice in 3 times Neptune's orbit. So those resonances are real things, and it's exactly as Evan said. When the planets line up, they get a kick. They pull on each other, and that's what causes the resonances in the first place. And it's also what makes them stable. So Evan's question is, which arrangement is more stable in the long term? And it's the resonant situation. Maybe in a few billion years' time, we'll find that the orbits of the planets in the solar system have got more resonances, but it's the resonances typically are found in the smaller objects like Pluto, because they're easier for the gravitational pull to shift them into the relevant orbits.
So it sounds to me like this relationship between some of these orbiting bodies is a natural state, and very, very common by the sound of it. It brings into question the mysterious planet 9. If it's out there, whether or not it's a whole planet or a whole bunch of smaller objects, they too may well be in resonance or developing that kind of orbital pattern, would they not?
The thing about Planet 9 is, its orbital period is it's well over 1,000 years, and so that means it's only gone round 4 million times or something, and that might, I'm doing this in my head at the moment, that might mean that you've got not enough gravitational interaction, especially at that distance. It's at a huge distance from the sun if it exists. So my guess is that there wouldn't be many resonances found, although the reason why people think Planet 9 is there is because of the elongation of the orbits of some of the trans-Neptunian objects, to give them their proper name. The trouble is this: you can say Kuiper belt objects, but Kuiper belt objects are different from scattered disk objects, and they're different from resonant objects. So it's best just to say trans-Neptunian objects, and that's what they are. In fact, they're actually, technically, they're called ETNOs, extreme trans-Neptunian objects, the ones that are aligned.
Okay, I'm letting that one go through to the keeper. I can't do it again. Talking about the naming of objects by astronomers, they really need to engage a consultant, I think. Evan, thank you very much for your question. As always, appreciated. Let's move on to our next question, and this one comes from Simon in Melbourne. This is like black holes are a very common area that people want to know about, I guess because of the mystery surrounding them. We don't know a lot. But Simon's come up with an angle that I don't think we've actually answered fully in the past. So let's find out what he wants to know.
Hey, Andrew and Fred. Thanks for taking my question. It's Simon here from Melbourne. I've just got a quick question about the kind of production of black holes, and more specifically the exact moment that normal material becomes a black hole. It might be more of a mathematical question or a theoretical mathematical question. But if you've got a material which is not a black hole, but on the very edge of becoming a black hole, and then you put a little bit more mass into it or shrink the size of it. I'm more kind of asking what happens at the exact moment that material turns from being what we would perceive to be normal matter and into a black hole. I assume this is a one-way transition, and simply taking a little bit more of the matter away, if you were to hypothesize doing that, would it then not become a black hole? Although I appreciate this is not possible because nothing can escape a black hole. But if you're balancing right on the edge of the black hole and normal matter, I'm just wondering kind of what the physicality of this would be, and maybe the mathematics associated with it. So to summarize, if we've got normal matter and we pop a little bit more material in there and then it becomes a black hole, how does the transition work? Love the show. I hope you guys are doing well, and we'll look forward to hearing your answer.
Thank you, Simon. When does matter become part of a black hole? Is it an instantaneous thing, Fred, or are we talking something that happens gradually?
The short answer is it's effectively instantaneous, and it's not. There are when a star undergoes a gravitational collapse, it's actually the core of the star, the envelope, is kind of blasted off usually as a supernova explosion. So you've got this core, which has, if its mass is more than about let's do it in stages. If its mass is about the same as the sun's mass, it'll collapse to be a white dwarf star, which is a state of matter. It's not normal matter by any means, but it's not a black hole either. That's where the electrons, it's just the outward pressure of the electrons that's stopping it from collapsing further. And so that's balancing the force of gravity. If it's bigger than 1.4 times the mass of the sun, then the electron pressure isn't enough to stop the collapse. And the collapse will turn into a neutron star, where it's the neutron pressure that's basically pushing things apart. Those different stages, as I said, they're not normal matter, and it's that collapse is instantaneous. What's stopping the collapse in a normal star is the outward pressure of the radiation. But when that switches off, then gravity takes over, and gravity is all powerful. It's even though it's the weakest of the four fundamental forces, it's a force to be reckoned with. And so that's what pulls them down to these degenerate states of matter. If it's more than we think at the moment, it's 2.2 times the mass of the sun. Some people say about 3, but there was some work done last year that looks like 2.2. Then the collapse doesn't stop. And in an instant, literally in an instant, it goes into a singularity and you've got a black hole. So it's not a gradual process. And it's also not a process that you could take normal matter and add a bit to it, because if you did that, you'd get a white dwarf. You'd get electron degenerate matter, as it's called. So, but the bottom line is it's a very rapid process, and not something that I'm saying we've never observed it. And the odds, we see supernovae occurring, and when you get this brilliant flash of light that outshines its host galaxy, what you know is happening, if it's a massive enough star, is the formation of a black hole. But you can't see that bit. Maybe in time we'll have gravitational wave detectors that are sufficiently accurate to detect that. The problem with a black hole when it collapses is it's symmetric. It's a symmetric collapse, and that doesn't produce a gravitational wave signal. But if you've got one that's got slightly more matter on one side than the other, then it would, a star in that case. There you go.
It's all getting very complicated, Fred.
It's terribly complicated, that's why we're here.
Yeah, I mean, black holes, once they're formed, become quite hungry, and anything nearby gets, as you said, spaghettified. What happens to that matter?
It just becomes part of the black hole. That's the interesting.
So it adds to its wealth.
It adds to its mass. It doesn't add to its volume, because that is zero, essentially. In a true black hole, there might be weird black holes that it's not but it's zero by definition in a true black hole. So the volume doesn't change, but the mass goes up.
Yeah. Okay, my brain hurts now. But thank you, Simon. Hopefully that answered your question, as we say, adequately.
Yes.
Now, we've got plenty more to come. Sorry?
This show it's the hallmark of Space Nuts, adequate.
Yes. Yeah, what makes me smile, Fred, is people are now referring to themselves as Space Nuts.
Yeah, good on them. Yeah.
Yeah.
Nice to hear.
We've created a monster. Anyway, you are listening to the Space Nuts podcast, and if you're a YouTuber, you are also watching us, I'm sorry to say. With Andrew Dunkley, Fred Watson, and our special guest today is Russell Palmer.
0G, and I feel fine.
Space Nuts.
Thanks for joining us on the Space Nuts podcast. Andrew Dunkley here with Fred Watson and Russell Palmer, our special guest. We'll get to Russell in a moment. Just wanted to remind you that if you want to become a patron, that's easy to do. Just go to our website and click on the Support Space Nuts button, and you can find out how to become a patron. You can do that through Patreon. You can do it through Acast, which is our prime carrier for the podcast. You can do it through Supercast, and there are all sorts of packages and options available. It's not expensive. It's not mandatory either, but we do want to reach a point in time where the podcast is fully supported by the audience, and so becoming a patron is the way to do that. And it can cost you as little as $3 a month, but if you want to buy in for a year, you can do that. And we've had a couple of people do it in the last week or so. So thank you to you. It's just fantastic. Ashley is one of those. We got a lovely email from Ashley. We answered his question a couple of weeks ago from Atlanta, Georgia, 9-year-old. And Ashley has used his pocket money to pay for a 1-year subscription to the Space Nuts podcast, which I think is fantastic. I feel terribly guilty for taking your money, Ashley. But look, it's great to have a fan who's so thrilled with the podcast that he's willing to do that. So thanks, Ashley. It's fantastic. And we've got another question from you, which we will try and get to in coming episodes. But that is awesome. But if you'd like to become a patron, that is easy to do. Just go to our website, spacenutspodcast.com, click on the Support Space Nuts button, and go from there if you so desire. We do want to try and get to 1,000 patrons, because then we can become self-sustaining, which is the whole goal, and just keep on producing the program for as long as we possibly can, until a black hole comes along and really deals with all that. Now, I'd like to introduce you to Russell Palmer. Russell is a space nut. Has been listening to us for quite some time, 5 or 10 minutes now, I think it is. And Russell is our first live studio guest. Russell, I think I should ask you firstly where your interest in space science, astronomy and astrophysics all came from. The questions you've sent us are not only many, but they are very, very... I'll use the word complicated, because they are to me. Where did it all start for you?
It started, Andrew, in 1973, when I was doing my honours year as a physicist at Monash University in Melbourne. And my project there was on a telescope which had been donated to the university. It was called the Jeffrey Telescope, 16-inch Newtonian. And I think it's still situated out at Emerald. My job was to work on the standardisation of a UBV photometer on that. But that job, or that period of my life, got me hooked on astronomy. I've been very interested ever since. I pursued a career in the Air Force, and subsequently I've worked as a diver, and now I'm still working for a mining company, adjusting schedules to take care of breakdowns and things like that. So, yeah, my job is I think I regard myself as a trained problem solver, and that is still my job.
Fantastic. So, oh, wow. Well, we suspected you were an astute fellow, and given your educational history, it's not surprising when we receive your questions that they seem so very involved. And what part of WA are you in? Is it Bunbury?
Well, it's very close to Bunbury, about 30 kilometres down the road, in Donnybrook.
Oh, that's right.
So we're far enough out of all the towns to have beautiful clear skies here.
Yeah.
It's great, yeah.
Yeah, great place. Okay, Russell, Fred is eager, willing, and hopefully able to deal with some of the things you want resolved. So fire away with your first question.
Well, I just want to say I'm totally blown away to be on this show, and fantastic to be invited. But this question really, it's Fred's fault. He mentioned a few things which got me thinking. So I want to talk about the role of quantum fluctuations in the expanding universe. And I have to read some of this, it's a bit complicated, as you say, and I just hope I can do an interesting job like Stuart Gary does. So anyway, when I was young, space was the big nothing up there. But come to learn that space is not nothing. It has some remarkable properties, in fact. It sets a speed limit on all things, and space transmits light in all directions at the same speed, no matter how you're looking at it or how fast you're going. And space is incredibly elastic. It went from nothing at the start of the Big Bang to the humongous thing it is now. It gets screwed up by quickly rotating massive objects, but it never rips, never tears. And it can hold black holes of infinite density in a single point. So it's amazingly elastic. And space supports quantum fluctuations. So all of space can do all these things. It's not a localized thing. It's a uniform. All these properties of space are uniform. So when Fred explained the way black holes evaporate by one of a virtual pair of produced in a quantum fluctuation, removing the energy of its creation in the real universe from the black hole, this gave me an idea that space may have yet another property, and that is a cosmic binding energy as part of the fabric of space. So it may help to look at the cause of the expansion of space the other way round to what we've been doing. So quantum fluctuations are not just near the event horizons of black holes, they're everywhere. And all of space is filled with them.
He's only got 4 pages to go, Fred.
Half a page more, but it's thick writing. Virtual particles of matter and antimatter are believed to be created spontaneously without a source of energy. But this violates the conservation of energy for anything that lasts longer than the uncertainty principle permits. So is it possible that the energy is borrowed from space itself for the brief interval of their existence and is given back to space when the particles annihilate? The cumulative effect of these particles are measurable, and we need to account for them. So, could the cumulative energy which these virtual pairs borrow for their moment of near existence add up to the loss of some of the binding energy of space itself? So at any one time, there's a certain amount of this energy being taken out of space by umpteen squillions of these virtual pairs. So this ongoing temporary loss of some of the binding energy would allow the fabric of space to disperse, not be pushed apart, but dispersed. It wouldn't be pushed apart by an ever-increasing dark energy, which is another violation of the conservation of energy, but would simply be dispersing through the cumulative loss of some of space's binding energy. So when viewed in this way, the expansion of the universe, which is the total space, is consistent with the brief period of cosmic inflation when most of the matter in the universe was created in the Big Bang. This would mean that the Big Bang has never stopped. It's still going on. The expansion of space is simply the Big Bang ongoing with the creation of substantial matter from space having been largely replaced by the temporary creation of virtual matter. This theory does away with two violations of the conservation of energy present in quantum fluctuation theory and dark energy theory. It explains the expansion of the universe away from other binding forces through the well-understood second law of thermodynamics, or which is, what do we call it? Anyway, the second law of thermodynamics acting on the relaxing fabric of space. It explains the acceleration of the universe, of the universe's expansion through the action of quantum fluctuations in an ever-increasing volume of space. And it recognises the relationship between the cosmic inflationary period of the early universe and the creation of matter. Well, Fred, what do you think?
Well, I think that's too hard, and we go to the next question.
Okay.
Yeah, so what you're saying is it does have some resonances, I think, with some of the work that particle physicists do on this problem. You know, it's all about looking for the nexus, the connection between these two disparate theories that govern the universe, quantum mechanics and general relativity. And so there's a huge amount of work that's been going on ever since both those two theories appeared on trying to reconcile them. And certainly a lot of what you're saying is the sort of thing that the particle physicists say when I'm talking to them. I'm not a particle physicist, so I listen with great interest. But I think the approach that you're taking, I think when you do the mathematics, I think it's the same as the one, and it's all about quantum fluctuations. If you go down that path and you look at the net result of that on a large scale, you get an answer for the expansion of the universe that is 10 to the power 120 times too big. It's considered to be the worst prediction of theoretical physics, because the universe would have ripped itself apart within the first microsecond if that was the case. And so it's an avenue, I think, that a lot of people have stumbled over, and they're the ones who are putting the mathematics into it. And that's something that certainly the mathematics of quantum theory, I know it involves Hilbert spaces, which are an abstract algebra construct, and I dealt with things like that when I was an undergraduate, and they did my brains in, Andrew, just like a lot of this stuff does yours in. So that the mathematics don't work out. That's the problem. You're probably aware of the Casimir force as well, which is a force of the vacuum itself, and it's demonstrated. You can show that if you've got two plates in a vacuum and bring them close together, they will actually repel. And it's because of these quantum fluctuations taking place in the gap between them. So there is experimental work done on that, experimental understanding. But I think it's the people who've looked at this kind of thing, I think, have had problems with this ridiculous number, 10 to the power 120 times too big. It's really quite embarrassing. That's why we don't talk about it on Space Notes, because we're embarrassed enough already with dark matter and dark energy.
Yeah. That repelling force you mentioned, I have the same effect when I'm holding money.
It just leaves. But look, what I would do, Rusty, is I think you'll find... Oh, that's terrible. I hate saying that. It reminds me of old men telling me about... So I think you'll find it's a 259cc engine, not a 300cc engine. But you will find plenty of material on the web, and mostly from physics departments around the world where they've looked at this kind of problem. One other thing I like in your question is how incredibly flexible space is. And it is, you're right, it bends. However, by terrestrial standards, it's not. And you will know what the Young's modulus is. It's the amount of stretchiness usually measured in a wire. So the Young's modulus of space, it's how flexible it is effectively, is 100 billion times stiffer than steel. So it's pretty rigid, and that's why it takes huge gravitational masses to bend it at all. But of course, when you're next to a black hole where you've got this incredible gravitational pull, it does seem very, very flexible, enough to spaghettify anything as well. Great stuff, though. I love all that.
Fabulous.
I wish I'd taken more notice of quantum physics when I was at uni, and I have to say, a lot of that went right over my head in those days. But of course, this was back in 1965. So. There you go. I had other things on my mind then.
I think I had porridge on my face at that point in time, or something. Yeah. Anyway, how did you go, Russell? Did you sort that one? Was it adequate?
Yes.
Yeah. I'll have a look and see if I can, find anything that's comparable with what you're describing, and this 10th of power 120, where that comes from. The numbers are incredible. You probably know I'm writing a book for kids at the moment for the 8 to 12 year group, and that suits me very well because I think that's about the level I am. So I've had to look up things like how flexible space is. I've had to check out all these figures, which is why they're all in front of my mind. I'm not going to mention the 10th to the power 120, though. That's just too embarrassing.
Okay. Now, Rusty, did you have any more that you wanted to bring up?
I have some more, I have to say, a bit more mundane questions, but...
we might see if we can tackle one or two, time permitting.
Okay, well, this one's about the search for Planet 9, which has already come up in the program, so I guess it's topical. But I'd like to look for Planet 9 the other way around as well. So is it possible to examine Fred's survey data on stellar radial velocities for an unexpected blue hump in the data in a region, so that a gentle blue shift in the background stars would indicate that the telescope is being pulled towards them unexpectedly? And I think that this would be a fraction of the tug something in the region of the Earth would get from the gas and ice giants, not to mention the moon, the travel of the Earth around the sun, and the travel of the sun through its orbit around the centre of the galaxy. But if it's compared with the blue shift of stars 20 or 30 degrees away, there could be a difference if there's a Planet 9 out there giving us a pull. So what do you think of that one, Fred?
The gravitational effect of Planet 9 on the rest of the solar system is when you're thinking about what you're describing, it's infinitesimally small compared with the normal differences in the radial velocities of stars that we see just because of the rotation of the galaxy. So this was all looked at in the 1920s and 30s, if I remember, by Jan Oort. Of Oort's cloud fame. He's the guy who proposed this cloud of comets, but he also looked at the speeds of stars in the solar neighborhood and deduced from that you can actually tell that the galaxy is rotating, because when you look along different lines of sight, the characteristic rotation of the galaxy imprints itself on those velocities. Of course, stars have their own, what we call peculiar velocities as well, their own speed that's sort of superimposed on the galactic rotation, a bit like galaxies do on the Hubble flow. But any acceleration that will be due to Planet 9 will be, I think, immeasurable on the kind of scale. We do look, nowadays, velocities can be detected which are far less than walking speed. They're centimetres per second, and those are the techniques that are used when you look for planets in orbit around other stars. But they're with very specialised equipment. You don't do large-scale surveys with those. So I don't think there's anything that would reveal it. If an object, the way we're going to find Planet 9 if it's there is by its motion across the line of sight, which will be very, very slow. And so that's the difficulty. You're looking at these star fields and you're looking for something whose movement is only detectable after a couple of months or something like that, even more perhaps. But that's the way it will probably be found, and it may never be found. And just to tie up a few loose ends there, some people think that if Planet 9 is there, it's not actually a planet at all. It's a primordial black hole that is having this effect on pulling these orbits of the trans-Neptunian objects, but it's not really a planet, so we'd never see it. So it might still be there and be completely invisible. We don't know whether primordial black holes exist. They're black holes that may have been created in the Big Bang, probably by quantum fluctuations in nothing.
Maybe so. All right.
Got a few different strands together and goes deeper into the mire.
In any case, it can't be a planet, can it? Because its orbit is so slow, it could no way have cleared its orbit of other bodies.
Yeah, that's a good question actually. It could even have its own Trojan asteroids, like Jupiter and Saturn do. But actually, it's not Jupiter and Saturn; it's Jupiter and Neptune, I think. Anyway, another meander. Sorry.
No, that's all good. It's all good. Meandering is what we do.
Rescue us.
We're very good at it. How are we going for time? Have you got one more quick question, Russell?
I do, and this is about out of zodiac telescopes. Telescopes that
I thought you were going to talk astrology there. I nearly panicked.
Positioned out of the zodiac. Okay, so the idea is we seem to have trouble seeing city killer-sized asteroids because they're small, relatively small, and can be lost in the zodiacal light. It also takes a while to get a fix on these and plot their course. So maybe in the future we could orbit three telescopes at equidistant around the Sun in a solar polar orbit, which takes them right out of the zodiac to overcome these limitations. 3 would guarantee that 2 were always clear of the zodiac if they were equidistant, or the plane of the solar system. And 3 could be used for 3D interferometry, quickly determining the position and the velocity. The arrangement would also be good for astrometry, I would say. I know this would be expensive and years away, but would it be worthwhile, Fred?
Yeah, actually, that's a great suggestion. People have talked about things like that, but there's a sort of consensus on this, but there isn't a spacecraft yet planned for it. But one possibility that would probably help a lot with exactly the kind of near-Earth objects that you're talking about, the ones that come to us out of the Sun effectively in the plane of the ecliptic, if you put a spacecraft at the Sun's second Lagrange point, the L2 point, that's the point between, I beg your pardon, no, it's the L1 point, not the L2 point. The L1 point, it's the point between the Sun and the Earth where the gravitational force is balanced. And so there's that stable point there. And if you put a telescope there looking towards the Earth with a very wide field of view, then you've got a good chance of seeing things, partly because you're always seeing your objects in the full glare of the Sun. They're being back illuminated by the Sun being behind you in the spacecraft. Not humans, but robotic spacecraft. So it's one of the ways. There is a foundation, I think, which is trying to raise money to set up a facility like that, and that would be great. The 3 spacecraft equidistant, and they would also probably have to be at Lagrange points, but different ones, would be the Rolls-Royce solution. But the one in between ourselves and the Sun would be a great step towards seeing these smaller objects, exactly the ones you're talking about, 15 meters across, that would damage a city like Chelyabinsk in Russia back in 2013, that kind of thing. We're really not well warned against at the moment, although the things like Pan-STARRS and the other near-Earth object facilities do an incredible job. Some of the objects have picked up are only 2 or 3 meters in diameter, and they just disappear into space. But it's so things are improving. But something like a spacecraft, an NEO spacecraft, will be great. So I can't remember. 360 comes into my mind, but that might be a completely different foundation altogether. But it's something like that that's looking at this possibility.
Mm. All right, Rusty. Thanks so much.
Many thanks, Rusty.
You've got a great mind. It was really good to sort of get it from the horse's mouth, if you like, in terms of what's puzzling you and some of the theories and ideas you've come up with. Fantastic. Really enjoyed it. So sit back, relax, take a breath. The hard part's over for you.
Go back to sleep.
But yeah, thanks for being a part of the Space Nuts podcast, which you are listening to and watching with Andrew Dunkley, Fred Watson, and Rusty Palmer.
Thanks for having me.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Welcome back. You're listening to the Space Nuts podcast, episode 240, with Andrew Dunkley and Fred Watson, and our special guest today is Rusty Palmer from WA, which is on the other side of Australia. It's from where I'm sitting, it's that way, to my right, which means I'm facing south. Is that right? Yeah, it would be.
Yes.
Okay. Yes, and it's good to have Russell along. He's asked some really good questions. Astute. I like that word. Now, a reminder too, if you'd like to follow us on Facebook, you can do that by logging on to the Space Nuts Facebook page. Just do a search for Space Nuts Podcast on Facebook and join us there. We've got a lot of followers there now. We're really building a really big follow. I think it's somewhere around 2,500 people that are on our Facebook page now. So please join them and become part of that community. You can also join the Space Nuts podcast group on Facebook, which is a group that was created by Space Nuts listeners. So you can all chat to each other and fire off some questions and answer each other's questions, come up with theories and ideas. And I love the way you police everything. Sometimes we'll get an infiltrator in there that is trying to, I don't know, sell watermelons. Generally dealt with rather quickly, I must say. It's fascinating to watch. But anyway, we're on just about every social media platform. Of course, we'd love to add to our YouTube numbers as well. So if you prefer to watch as well as listen, find us on YouTube, Space Nuts Podcast. There's all sorts of options. And thank you for supporting the Space Nuts Podcast in whatever way you do, and for listening to us. Our numbers are just growing, and we are just so humbled by the support. So thank you very much. Now, to our next question, Fredo. This comes from Martin now, here we go. When I was growing up, I lived near a dam we called Chichester Dam. Now, is it Chichester or Chichester?
It's Chichester, Andrew. Yes.
Okay. I'm writing from Chichester, which is on the south coast of England and also the birthplace of astronaut Tim Peake. I've been thinking about the ancient light that reaches the Earth and allows us to see back in time to the early universe. Will our ability to see back in time reduce as light from the early universe travels past us? Or maybe, if the universe is infinite and expanding, is there light from the early universe that will never reach us? Hope that makes sense. Thanks for a great podcast. Martin. Thank you, Martin. Oh, ancient light. Where's it going? What's it doing? Have we seen it all? Will it disappear? Will we all end up in total blackness and never wake up? What's going to happen?
All of those, Andrew.
Oh, great.
Yeah. No, Martin's right. That because the universe is expanding, and we think its expansion is increasing, ever increasing. That's been demonstrated by the many observations in recent years, since 1998, when it was first observed by people like Brian Schmidt and others. I'm sorry, there's a truck reversing outside my door.
Fred lives next to a veterinary surgery, and they're probably taking away a horse that didn't make it.
Do you know, that's exactly what that truck does.
You're kidding me.
Yeah. Not usually horses, but smaller animals.
Oh, dear, oh, dear.
That's the one.
Oh, I feel bad now.
Between you and me, Andrew, we call the delightful gentlemen who do that, and we call them the body snatchers. Yeah. Anyway, that's what's happening.
Yeah, all right. R.I.P. Fido.
So back to the universe. Talk about the sublime to the ridiculous. Or maybe the other way around.
We just turned Fido into a dog star.
Oh, lovely. Yeah.
Sorry.
Well, because the universe's expansion is accelerating, there will be a time in the distant future when, we won't see most of what's around us. The light will never reach us, exactly as Martin suggested. But there is already part of the early universe that we can't see. And that is what lies beyond the cosmic microwave background radiation, which is what I call the cosmic wallpaper. It's that background to the universe that is the flash of the Big Bang. You're looking so far back in time. You're seeing back to a time when the universe was still glowing brightly. Now, beyond that, there is more universe. And it may be, as Martin says, it may even be infinite. We actually don't know the answer to that question. But we know that there's a horizon beyond which we can't see, and lots of universe beyond it. And so, yes, the answer is that there are bits of the universe that we will never see, which is why you sometimes hear the expression, the observable universe, because that's the bit that we can see.
Okay. We talked about this fairly recently. What percentage of the universe can we actually see?
Well, we don't know, because we don't know how big it is.
Oh, that's true.
So you can't put a percentage on it. And
we can see 100% of what we can see, but not even that.
Yeah, that's right. Yeah.
Other things, but we don't know how much is beyond that. That's one of the great.
It's all about. It's what Rusty was talking about earlier. It's about the inflationary period of the universe. Within the first 10 to the minus 32 of a second, took it from being the size of a hair to the size of a galaxy in that length of time, and that's a reasonably well-established phenomenon. It's the only way to explain certain aspects of this microwave background radiation. Eventually, we might see the gravitational wave signal of that as well. So the expansion period is when the universe got big, and that's why we think there's a lot more of it beyond what we can see.
And what do we think might be out there? Just more galaxies?
More of the same.
Yeah.
More of the same, yeah.
It's all the same. It's a boring place. All right. Thank you, Martin. Hope that helped. Let's go on to our final question for this episode, 240 of the Space Nuts podcast. This one comes from Sandy in Melbourne, who, when looking up at the International Space Station, wonders why it blinks.
Hi, Fred and Andrew. This is Sandy Fernando from Melbourne, Victoria. First of all, great show. I only recently started listening after my brother recommended it. Now I'm totally hooked, to the point where I've started going through your back catalogue while I'm waiting for the new episodes. I have two questions. When the ISS transits across our sky, I have noticed it blinks out. This usually happens at the end of the transit, and in particular when the visual part of the transit seems to be only covering part of the sky. Why does it blink? Is it similar effect to the old iridium flares? Second question. Recently I came across an article which was talking about radio signals detected by the Parkes Radio Telescope in 2019. It was potentially a new WOW signal the article talked about. Are you able to tell us more about this finding? Is it similar to the original WOW signal? Thank you, and keep up the awesome show. Really looking forward to each episode.
Thank you, Sandy. Great to hear from you, and good questions. I suppose we'll tackle the first part first, which is the blinking out of the ISS while observing it in orbit. Why would that happen, Fred? Saving energy, turning the lights off. The kettle drags too much on the battery.
All of the above. Of course, the ISS shines by reflected light. It doesn't have any lights on it. There are probably lights in the windows, but they wouldn't be bright enough for us to see from down here. So it's just the reflection, and the reason why it's so bright is because it's such a big object. Now, I'm assuming that what Sandy means is that its brightness increases before it disappears. That's how I'm interpreting blinks out. Because you would expect it to disappear when it goes into the Earth's shadow, and indeed that's what does happen. Usually it's not just switching off. It's a more, a little bit of a gentler decline in brightness, and that's because you're effectively going through the twilight zone briefly, as at 8 kilometers per second. It doesn't take very long to get through the Earth's penumbra, the outer part of the Earth's shadow, but it does happen, and so there's a drop in brightness that is not instantaneous, but doesn't take very long either. If you can see a blink before that happens, I guess it could be a reflection from one of the solar panels, because the big part of the space station is these huge solar panels that it's got. They're enormous, and if they're tilted at the right sort of angle, and they would be pointing roughly towards the sun, maybe as it gets low on the horizon there might be an increase in brightness, but I haven't heard that reported before.
That probably makes sense. It's sort of not unlike the sun reflecting off an aircraft that you sometimes see, or
Yes.
a car coming towards you. It happened to us on the Murray River. A boat came around the corner, and the sunlight hit the exact right part of the windscreen, and it looked like two headlights heading towards us just for a moment. It was, that could easily be the reason.
Yes. That's what I would put it down to, and as Sandy says, it's a lot like the old Iridium flares. Iridium was a family of 66, I think, spacecraft that had things like full-size bathroom mirrors, which were its antennas, and when they caught the sun, you get this very bright patch of light. They're being phased out now. In fact, they may all have been deorbited, because there's a new type of Iridium that doesn't do that, but they were very spectacular. Maybe that's what it is.
Okay.
So,
now, the second part of the question is in regard to the potential second WOW signal detected by the Parkes Radio Telescope in 2019. I got a feeling we talked about this.
We did. That's right. So it's there is something going on, and I'm really annoyed with myself because I was talking to a colleague of mine who I know very well, who's at Parkes, works at Parkes at the Dish. Last week I was talking to him about something completely different, and I never thought to ask him about this. I wish I had done. But yes, we have informal knowledge of some sort of detection with the Parkes Dish, which has been, it's carrying out one segment of the Breakthrough Listen project, which is specifically looking for alien signals, blasts of radio waves, with either the Parkes telescope or the Green Bank Observatory in West Virginia. And they've been going since 2015, I think, not really found anything. But apparently, and it was, I think, in 2019, there was an event that is of interest, and it's been given a name which I can't find in my notes here. Something like, I think it's BLS or something 1, Breakthrough Listen Signal or whatever. It's at 980 megahertz, which is what the telescope was looking at the time, and it's from the direction of Proxima Centauri, the nearest star. However, the Parkes Dish it doesn't have that kind of accuracy that you can't rule out many background stars as well. So it could be coming from a lot further away. Yes, it's BLC1. I'm not sure what the C stands for in the Breakthrough Listen signal. Anyway, it is of interest because it looked as though there was a shift in its frequency, which you would get as a planet goes around its parent star. And that's why people are a bit interested in it and excited. There's a really good chance that it will turn out to be something pretty mundane, a signal from a terrestrial source. But as we understand it, there is a paper being written about this, which hasn't yet been published. There was a piece in The Conversation recently written by the director of the Centre for Astrophysics at the University of Manchester, Michael Garrett. So he's pretty well up there in terms of the inside knowledge on this. What he says is in his Conversation article is that the discovery, which was reported by The Guardian but has yet to be published in a scientific journal, may be the search for extraterrestrial intelligence's first bona fide candidate signal, and has been dubbed Breakthrough Listen Candidate 1, or simply BLC1. So I think you've got to watch this space. It's interesting. There's a really good chance that it'll turn out to be something else. Read the Conversation article if you are interested in following it up. Look up Michael Garrett and The Conversation, and it will take you there, and you'll find out all that we know about it.
Fantastic. Thank you, Sandy. Great questions. Of course, the WOW signal we've talked about before, that radio signal that was received, and the person who detected it wrote "wow" with an exclamation mark on the printout. Hence the WOW signal, which they still haven't explained, have they, Fred?
No, I should have said that. Sorry.
No, that's okay. It's just it's one of those mysteries. Yeah, we did do a whole segment on it. Yeah. I think we talked about it back in 2019 when this topic first came up. But yeah, thank you, Sandy. Thank you, Martin. Thank you, Simon. Thank you, Evan, for your questions. Thank you, Russell, for being a part of the show. It's been great.
It's been a pleasure, an honour. Thank you.
No, it's terrific. I hope you enjoyed yourself. It's a little bit different on the inside, isn't it?
It is.
You can see how very professional we are.
Yeah. I bet Rusty stops listening to us now. I think. It's a whole lot of rubbish.
Yeah. Oh, dear. Anyway, that brings us to the end of another show. Thanks, Rusty, again. Thank you, Fred, as always. Great fun. Nice to catch up again.
Always good to talk, Andrew, and thank you very much, and we'll speak soon.
We will indeed. Fred Watson, Astronomer-at-Large, and from me, Andrew Dunkley, thanks as always for listening to, watching and supporting the Space Nuts podcast. We'll catch you again real soon. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.